Not able to get my iPad in here.
Okay, then in the meantime, welcome to the February workshop. So today we'll be going, okay, today we'll be going over bronze and silver. So bronze will be from 6 to 7 PST, and then silver will be from 7 to 8 PST. And then if we finish early, we'll take a break in the middle. So problem 1 and 2 will be shared by Waymo from xcamp, and then problem 3 will be shared from Andrew. So as soon as Waymo finishes, or gets technical difficulties done, then we'll start.
Wait,
And then,
I'm gonna leave the meeting temporarily and see if that fixes the issue.
okay, yeah. And then if you guys have any questions during the presentations, you can feel free to message in chat, and it'll be included in the presentation.
Well, hello? Can you hear me?
Yeah,
Okay, thank you. I'm gonna tr Give me a second. Okay, I'm gonna try to make a whiteboard and see if it works because we had an issue with the whiteboard last time. Okay, I think this works then. Okay, then let's just start with the problems. So let me send the problem statements in the chat. Give me a second. Sorry if the images are a little small. Yeah, okay, so here are the problem statements in the chat. So I guess we'll start from problem one, which so the problem statement's like this. So Bessie and Elsie are playing a game where where they have a pile of S stones, and in each move they can pick some integer X, such that X is not a palindrome, and then they'll remove X stones from S. So they set S is equal to S minus X. And when if a pile is empty when a if a pile is empty when a cow's turn starts, then they lose. The funny thing is that this game is commonly known as NIM, where of course the rules can vary between game to game, but for instance, the variation where each time you can remove one, two, or three um stones at a time, something like that, is a commonly known problem for just like computer science in general. So but in this particular problem, you can remove any number that's not a palindrome. And in particular, they said that leading zeros are not allowed. So as in the statement, they have uh, e.g. 990 is not. Oops, accidentally is not a palindrome. But then they also gave that this 121 or 1 are. So if you don't know where to start with this problem, right, it's hard to know exactly where to jump in. And it's hard to make a it's hard to like have find a direction of where to go in this problem. Of course, if you've seen something similar before, that can help, right? So, for instance, uh, one of the most important problems when it comes to games between two players is this idea of parity. And th there's or there's a sense in which like we can determine for a given number who is going to win, whether the first player that's going to move on that state is going to win, or the second player that moves on that state is going to win. And there's a sense of parity. So the most important observation for this problem is that in theory, in theory, uh, assuming that LC can, or assuming the second player can win. If the second player can win, then they can win only using numbers from, yes, this is the first bronze problem. They can win only ever choosing X or their palindrome as a number from 1 to 9. So this is the most important observation in this problem, which is that at least only from the perspective of the second player, they can win only using the numbers 1 through 9. So let's see exactly how that plays out and like how that idea is helpful. So for instance, let's consider if we started at say 30. Yes. So say we start at 30. And just like I'm gonna throw this out there that the second player can win from this if the starting pile has 30 stones. And I'm demonstrating that is that like for instance, if Bessie picks to use 11 picks 11 stones out of her pile, we'll be left with 19 stones. And then, for instance, Elsie or the second player can pick 9 stones, which leaves us at 10. And it's clear that no matter what move Bessie makes, or no matter what move the first player makes, the second player can choose the number. The first player takes X. The second player can take 10 minus X, and it'll be so this will leave us with 10 minus X stones. This will leave us with 0. And then you can see that the first player obviously loses. What just happened? Just broke something. Okay, I'm not quite sure what happened just now. Okay. This is bronze P1. Uh, wait a minute. Sorry. Yeah, so where was I earlier? So I had 30 to took 11 stones. This took us to 19, 9 stones to 10. And we have took X stones to 10 minus X. Then we took, and then we'll take 10 minus X stones to 0. So for instance, and then we can label this. This is, or rather, so I'll label F for the first player's turn and S for the second player's turn. And you can see that, like for instance, in this particular game, the first player loses, and the second player only ever used stone amounts from 1 through 9, right? And like the point of this observation is you can notice that for the second player, if if initially or yeah, if initially the first player's if initially the last digit of the first player's starting number is 0, the second player can guarantee that starting number will be 0 by the time the first player acts again. So essentially, if the number is some number of strings and it ends in 0, and this first player takes some number X, no matter what valid X the first player picked, the second player can leave it back to something, something, something ending in 0 for the first player's turn again. Um, and the way they do that is they take this X, and this X they can take the last digit of X, and they'll pick the number 10 minus X mod 10. And the way, and how this is possible is because there exists no palindromes that end in 0. So what this means is that if the last digit of the first number is 0 initially, the second player can guarantee that no matter what the first player does, the last digit will always be 0 whenever the first player acts. So it'll be 000 something and then 000. And you can see that the number is getting smaller over time. So which means that eventually the number will just be 0 and it won't be the second player's turn. It will have to be the first player's turn. So if the number initially ends in a 0, the second player can always win. They can always guarantee a win by forcing the first player to have to make a move starting from the last digit being 0. And the flip side of this is that say the starting value is not 0. Say we have like uh starting a value of 1, 2, 3, 4, 5, right? Then the first player actually can make the situation can make it into a pile where the last number is 0, and they're now the second player. So this is the first player, or yeah, this is the first player, and now it's the second player who has to make the first move on a pile of stones that ends in 0. So what this means is that in the case where the last digit of the number of the initial pile is not 0 initially, the first player can make it 0 after one move, and then the second player will be the one that loses. So after this seemingly complicated explanation, the solution for this problem is simply checking if the last digit is 0. Uh, if S mod 10 is equal to zero, then the answer is LC. The second player will always win. And then else Bessie. And at heart, that is just the solution to this problem. Noticing the most important part is noticing that we can conserve the value of the last, we can conserve the value mod 10 of the last digit as the second player. And essentially only the palindromes 1 through 9 count. Yeah, so that's the solution for this problem. Are there any questions or I don't know what's happening to the whiteboard because I don't know why it suddenly turns black, but if not, I'll move on to the second question. Oh, interesting. It's possible. So one, oh, I guess I sh should have elaborated on this more. Is that you can notice that in the problem they say that s is less than 10 to the power of 10 to the fifth. So it's 10 to the power of 10 to the fifth. And what this means is that you can't actually input the integer you can't actually input it as like an int type or a long type because 10 to the power of 10 to the fifth is very large. It's one with 10 to the fifth zeros after it, right? So you had to input the number as a string, and then use that to check whether or not the last digit is zero. I think and you can notice that in the last three test cases, they actually don't know how to write Python that well. But you can notice that in the last three test cases, the input string can be very large. Yeah, which is why that might have been an issue. Okay. I don't know what's happening to this whiteboard because this happened last time. Wait, give me a second. Oh my goodness. Because I remember last time we had the issue when this whiteboard was uh, but this whiteboard wasn't letting you write on it. Okay, this is really unfortunate. Oh, okay. Sorry, I'm having technical difficulties again. Oh my goodness. I don't know why it suddenly switched back to one of the new whiteboards instead of the classic ones. Sorry, let me figure something out for that. Sorry, technical difficulties. Okay, I don't know what happened to the Zoom whiteboard, but I'm gonna try to screen share to an online whiteboard instead. Really don't know what went wrong with Zoom all of a sudden. Oh my goodness, this is very unfortunate. Ah, okay, this works. Okay, so now for problem two. Um, so in this problem, you have n cows that are standing in a circle, right? And each cow initially has A of I amount of milk. And after 1 second, they're going to pass 1 unit of milk either to the left or to the right. And the question is, given all the initial amounts of milk and the direction each cow is going to pass their milk in, what is the total amount of milk that all the cows have after m minutes? And that's his question. So, I guess one of the important things is that first, so let's say we draw the cows like this. Alternatively, the cows might look like this. So the most important, or one of the important things is, for instance, if all of the cows are passing the milk in the same direction, then after 1 second, no milk will be gained and no milk will be lost. So in the event that this happens, then we know that I should oops. Yeah. We know that if all the values in S are the same, then the total amount of milk will be conserved. So in this case, the answer will just be the sum of A of I. And it wouldn't matter how many minutes pass, no milk can be gained and no milk can be lost. So we'll pretend that there exists no cases so we've covered all the cases where um like all the entries in S, as the problem statements call it, are the same. So okay, so then we'll notice that the problem statement actually looks a lot more than the case here on the left. Of course, it can be a lot more than that, but it'll look like you have a bunch of cows who are all passing milk in the same direction. And then you have two cows who are passing milk between each other. And there's another cow on the end, the other few cows on the end that are passing in the same direction. This is in general what it'll look like. So for instance, what you can notice is that first so this looks kind of like this, right? And you can notice what happens is that for these two circled cows, they'll maintain the same amount of milk because this cow will give 1 unit to this cow, while or so. this will be plus one, and this will be plus one. So in the course of a second, for these two circled cows, they won't gain or lose any milk. Alternatively, for this giant chain of cows, if you treat them all like as one giant conglomerate, they'll lose 1 unit of milk because this giant group of cows will try to send 1 unit to the circled cow, but the circled cow isn't accepting any more milk. So that unit of milk will be lost. And this will keep on happening for m minutes until either this group of cows runs out of milk or m minutes have passed and we've lost a total of m units of milk. So, yeah. And then, oops, probably should erase that. And you can notice that the same is true for this half as well. Is that this group, or of course here there's only one cow. This group of cows will also lose 1 unit of milk in the course of a second. And this also will continue until either m minutes have passed or they've run out of milk. So this is the crux of the problem. The crux of the problem is first off, determining what these groups of cows look like, and then summing up the milk contained by them, and then finally adding that to the answer. So let me erase this drawing. So another important fact is that since the cows are arranged in a circle, we can rotate both the array and the string by some amount, and the answer will still be the same. So for instance, in the first sample, it looks like RRL 331, right? But we can rotate this. Um, oops, it's not three, it's supposed to be one. We can rotate this, and the answer will still have to be the same because since it's a circle, it doesn't matter which point we start at, right? Okay, so now let's and also we know that the starting string, or yeah, the string is going to have at least one character that differs from the other. Um, of course, in the case it doesn't, we handled that case earlier. So what we can do is we can rotate the string. To implement the solution, we can rotate the string to some index such that s of n is not equal to s of 1. And I'll explain why this is helpful later. So we can first rotate the string to some position where that is the case. And then afterwards, what we can notice is that for each block of the string will now be split into blocks of characters that all have the same value. So for instance, we can have uh, a bunch of R's in a row or a bunch of in a row, or we do a singular L at the start. And in particular, the blocks don't go over the blocks like don't wrap around the string since we rotated our string in a way where that wouldn't be the case. And the other thing we can notice is that in a block, if this block, for instance, in this block of all R's, it looks like this, right? Where the cow at the very end of the block is the one is like the circled cow from the example earlier, that's gonna have its milk amount conserved. And then all the cows that are to the left of yeah, all the cows that are to the left of it will end up losing 1 unit of milk over the course of a minute. And similarly, if we have a block of L's, the cow that's on the very left is going to be the one that conserves the amount of milk it has. And then all the other cows to the right of it will lose milk over time. So we'll lose milk over time. So what we can do is we can first split up the string into these blocks, and then for each block, we consider the element on the very end and all the elements to either to the right or the left of it, depending on whether the block is R or L's. And we can first take this sum. Just call this sum, and then we can call this element X. Now what we can do is we can so for sum, oops. So for the sum, we can the amount that it'll add to the answer is either let me erase some of this stuff up here. So the sum will add oh goodness. The sum will contribute this much to the answer. And the reasoning behind this is that for every over the course of each minute, the sum will lose one value. So it'll be sum minus n. But it's impossible for you for this group of cows to contribute a negative answer to the total because when they run out of milk, they'll just stop losing milk. So it'll be the max of sum minus m and zero. And then as for the x will just contribute x units of milk because no amount of milk will be lost from this particular cow. So, and then similarly, here, this will be the sum, and this will be the x. So, yeah, and that's the total. So that's the solution for this problem. Of course, some careful implementation needs to be done to make sure you actually rotate the string correctly. But this is the final solution, and it should be O of n. And also note that due to the constraints of the problem, it might be necessary to use long or 64-bit integers to store the answer without overflow. Normally they'd have a bolded warning at the top, but I guess they didn't add any this time around. As for code, I'll send code later in the chat, but that's a or in C++, a long is a 64-bit integer. And it can store values up to 10 to the power, or it can store values up to 2 to the power of 63. Yeah. Or in, oops, my goodness, I don't know what's happening with my pencil. 2 to the power of 63. Yeah. So that's uh that's all for this problem. Yeah, I'll send code. I'll send code in the chat. And I think that that should be it from me, and the other person or Arvind will explain the third problem.
Okay, so we're going to be doing the third problem, maximizing productivity. So this is a problem if you want to be reminded of it. And then since you guys probably already read it, I'm just gonna give a quick summary. So Farmer John has n barns numbered 1 through n, and n is less than or equal to 2 times 10 to the fifth. And then we are given values called CI, which is the closing time of each barn. Bessie has to visit the barn before this time for it to count. Then there are given values called TI, which is the time between Bessie waking up and visiting barn I. Finally, we have Q queries from Bessie. Each query gives us her wake-up time and how many barns she wants to visit. We output yes if she is able to visit the amount of barns she wants to, and no if she isn't. The amount of queries is less than or equal to 2 times 10 to the fifth. Okay, so some observations we have is that we must have an n log n solution or better. And we have to answer each query in O1, around O1. You technically can answer each query in log n, which is what some people did with binary search, but that isn't necessary for bronze, so I'm not going to be going over that. Okay, so since we have to answer it in O1, we want to make an array of answers. So so basically what we do is we do subtraction to know when Bessie needs to wake up to visit barn I. After that, if we sort it from greatest to least, the indexes will represent how many barns we can visit. Okay, so we can go over a sample test case with this. So this is a sample input. So if she wanted to visit barn 5, she can't visit barn 4. I mean, this first barn, because 3 is less than 4. But this barn, she's able to visit. So basically, she wakes up at time 2, she can visit it, because 5 minus 2, you have to subtract 1 after, because you have to make it strictly before. Have 5 minus 2 minus 1, which is 2. We have 7 minus 3 minus 1, which is 3. Have 9 minus 3 minus 1, which is 5. And we have 12 minus 8 minus 1, which is 3. So basically, what these 4 numbers represent is if we sort them in from greatest to least, we have 5, 3, 3, 2. And these represent like how, like, if we get a number and then it's smaller than this, then she can visit 3 barns. Does that make sense? Thumbs up if it makes sense. Okay, I see a thumbs up. Okay, so basically, if she said that, oh, I woke up at time 3 and then I want to visit 3 barns, it's okay because this is index 3 if it's 1 indexed. But if she said something like, oh, I'm gonna wake up at time 4 and I want to visit 3 barns. 4 is bigger than 3, so that doesn't work. Okay, let's move on to the code. So the first step of this code is implementing basically what I said. So this code, it makes sense, and it should pass like the official USACO problem, but it's actually a little bit wrong. So here we have we get all the differences here, and then we sort it from greatest to least, and then if the answer of the index minus 1 is greater than equal to the barn she wants to visit, we output yes, and if not, no. But this is actually wrong because there's some cases where it's like uh minus, so like it doesn't cover every single one because answer.size is smaller than n. And then the actually correct code, which is a little modification, is this. So instead of just straight up sorting from greatest to least, we make a new answer array, and then we basically sort it from least to greatest, but we do it like this. Does that make sense? Does anybody have any questions? Yeah, I'll send the code later in chat.
Okay, so if you have any questions for any of the bronze problems, feel free to put them in chat. If not, then we'll take a break until 7 for the silver workshop. So feel free to message in chat. Okay, I think we can get started. So this is the silver workshop. We're going to present solutions for all three questions. So questions 1 and 3 will be presented by Arvind from xcamp, and then question 2 will be presented by Max Gang from CPI. So let's get started.
Sounds good. Yeah. So I'll start with question 1. Give me one moment. Give me 1 sec. All right. Yeah, so I'll share my screen. Yeah. So uh, so here are the silver problems. So so I'll start with problem 1. Um, yeah. So basically you're given a 2D coordinate plane. And there's n axis aligned rectangle targets, and there's 4n cows. And each cow must be assigned to a different target vertex. Um, yeah, and basically each target appears. Well, just like draw on the side. And there's 4 cows assigned to each target, right? So there's a bunch of targets that appear. And yeah, there's 4 cows that are assigned to each target, and each cow is on the y-axis. And it has some kind of slope, and it hits the target with that slope, right? And the cow is not allowed to pass the interior of the square that it's hitting. So if the cow, um, yeah, so if the beam is like this, it'll hit the interior. So this kind of not allowed, right? So each cow has some kind of slope with which it hits the target. Um, and you have 4n cows, and each one has some predetermined slope. And you want to assign the cows such that the difference between the top, the difference between the max y coordinate and min y coordinate are minimized. Yeah. And here we have n is up to like 4 times 10 to the 4th. Yeah. And the slope can be up to 10 to the 9. Yeah. So, yeah. So there are a couple observations we can make. So basically, if yeah, so if yeah, so I'll move to my OneNote. Yeah, so there's a couple of observations we can make. So given a particular rectangle, the cows that hit this vertex, or actually just the cows that hit the top right vertex or the bottom right vertex, there's a certain kind of property for them. So this cow needs to have negative slope. And then this cow needs to have positive slope. Right. And then finally, we want to minimize the difference between the max coordinate and the min coordinate. And we have the property in the problem that all of the x coordinates of the left edge are equal. So the squares, their left coordinates lie on this, they have the same x value, right? So if we consider the cows that intersect the y-axis. We consider the cows that intersect the y-axis and are matched to these vertices. We want to minimize the difference between the top and the bottom. So it's always optimal to put them in increasing order of slope. So when you go from bottom to top, it's always optimal to put them in increasing order of slope, right? Yeah, so those are some observations that you can get. So given for the top right vertex, you need to have negative slope. And for the bottom right vertex, the cow needs to have positive slope. Otherwise, it'll cut through the interior. And since everything in the left has the same x value, then it's always optimal if you want to minimize the difference between the top and bottom intersection to have the cows arranged in increasing order of slope, right? So you're already given the slopes beforehand. So that gives you that all of these have negative slope. Yeah, so all of these have negative slope and some suffix of this has negative slope. And then for the things with positive slope, all of these have positive slope and sorry, some suffix has negative slope. And some prefix of these has positive slope. Yeah, so now we have this observation. So we know how to solve for the subtask where the absolute value of SI is equal to 1 for all I, because if there are A cows with positive slope and then B cows with negative, then we know that there's n of them that are assigned here as positive, and then the top n minus A over here, oops, the top are also positive, and then B of them and negative on the right. So the bottom n minus B of them are assigned negative. Yeah, so we can solve for the subtask where SI equals 1. And now let's consider the full subtask where you can have SIs up to 10 to the 9. So essentially for the things with negative slope and the things with positive slope, you kind of have two independent problems. So you want to, yeah, so for the things with negative slope, you want to maximize the minimum intersection. So there's two things, right? So negative slope, I guess it's positive slope. Positive slope, these things are basically going downwards from the right. You want to minimize or you want to maximize the minimum intersection. And then for the negative slope, you want to minimize the max intersection. Yeah, I mean the max intersection with the y-axis, which is precisely the location of the cow. Yeah, so for positive slope, you want to maximize the min intersection with the y-axis. And then for the negative slope, you want to minimize the max intersection with the y-axis. So this, yeah. Yeah. So this is not straightforward to do directly, but what we can do is we can binary search on the answer. We can binary search on the answer. So yeah, so now we've split it into two independent problems. So we're only dealing with the vertices that have positive slope and the ones that have negative slope separately. So let's consider the things with positive slope, and we want to binary search on the the intersection of the lowest one, right? So we want to check if we can make all intersections greater than or equal to x. So we're basically binary searching on this x for the positive slopes, and then the maximum x such that this holds gives us the desired answer. Yeah. So if you want to check if it's greater than or equal to x, then yeah. So let's say we want to check if the max intersection or the min intersection is greater than or equal to x. If it's possible to have some kind of arrangement, right? So basically we have yeah. So for each point, so we're only dealing with the red, the things that come from the red points, right? So for the red points, we have an upper bound on the slope if we don't want to cross this. So basically all of these things with positive slope, we have an upper bound on the slope of what comes from here. So basically we have the slope can't be greater than or equal to a certain amount. So you have like all these upper bounds, right? So A1, A2, A3, up to AK. So you have upper bounds on all the slopes from A1. So if we want to check if we can make all the intersection values be greater than or equal to x, we can basically have upper bounds on all the slopes. And you can assume that these are all sorted. And then you take the actual positive slopes values. Yeah, so you take the actual positive slope values and you see if you can actually satisfy these upper bounds. And the way to satisfy these upper bounds is you sort the actual positive slopes to B1, B2, B3, up to BK. So just a reminder, these are the upper bounds for positive slopes. And these are the actual positive slopes. And these upper bounds are based on x. So we can achieve x whenever these values are less than or equal to the corresponding upper bounds. Yeah, so why is there an upper bound on the slopes? It's because we're binary searching on the minimum value, right? So we want to check if we can make all the intersections of the positive slopes be greater than or equal to x. So let's say that, so this is capital X, right? And then, yeah, you want to check if this intersection will be greater than or equal to x. And that gives an upper bound on the slope, right? So this is like y. Yeah, if this is y, then upper bound on the slope is going to be y over capital X. Is the upper bound the slope of the line between the vertex of the target and the cow located at x. So lowercase x is basically I want to check if the min cow coordinate will be greater than or equal to lowercase x for all the cows. Yeah. So basically, like I'm binary searching on this coordinate here, and I want to make the min coordinate as high as possible. And the one way that's one way that's doable to do this is by binary searching on what this value is. Yeah, I could have just called it T just to avoid confusion. Yeah. Okay, I'll call it T. Yeah, but basically the idea is that um the slope is going to be like y minus t. The upper bound for the slope that's connected to this vertex is going to be y minus t over x. So this slope here, if I have that the lowest point is greater than or equal to t, the slope must be at most y minus t over x. So basically I have all these upper bounds for the positive slopes. And I have my actual slopes, which I get from the input SI. And if I have these in sorted order and it's less than or equal to the upper bounds, then I'm done. I'm good. So basically we can binary search on the lower endpoint, and you want to try to maximize the lower endpoint. And you can binary search on the higher endpoint in a similar way and minimize the higher endpoint. Yeah, so basically binary searching on what's the value of the lowest cal, and then binary searching on what's the value of the highest cal. And just to summarize, we use the fact that we know which vertices have positive slopes attached to them, and we know which vertices have negative slopes attached to them. And we wanted to find the minimum and maximum intersections with the y-axis of these lines. And binary search ends up being a straightforward way to do it. Yeah. Any questions? Okay. Yeah, that's the solution for problem 1. Yeah. Okay. I guess I'll go over problem 2 and then yeah. Um, and then we can have the problem. Sorry, I mean problem 3, and then we can have the problem 2 explanation after that. Is this the hardest problem? I personally thought 2 was the hardest problem, but I think certain parts of the problem that are hard are like, I guess one part that's challenging is understanding the problem statement. Um, but I think after that, just like putting the pieces together, I think it's maybe one other thing that's tricky. I guess one thing that's tricky is just like making the observation that if you binary search on the answer, then that simplifies things a lot, because trying to do it directly can be very challenging. Like if you're given the positive slopes and you want to maximize like the minimum value, it's not clear how to, I don't know, it's not like super clear how to do it directly, but binary searching on the answer like um, simplifies that. How does the minimum y guarantee that the max y will be minimum? Yeah, so we know that the minimum y is going to be what are the possible values of okay, I'll answer that later. We know that the minimum value, since this vertex is red, um this has a positive slope. This has a positive slope, and the value of this is always going to be less than or equal to the values of negative slopes. What?
什么啊？
Wait. Um, yeah. So the minimum value is always going to be less than or equal to the intersections of the negative slopes. So it's guaranteed that the lower bound we get is going to be less than or equal to the upper bound we get. So the min value that we get from the positive slopes is always going to be less than or equal to the max value we get from the negative slopes. Just because the intersection of this with the y-axis has to be less than the intersection of this with the y-axis. Yeah, what are the possible values of t? Yeah, so to find the minimum value, you can binary search over t in the range some really small number. I don't remember the exact input constraints, but you might be able to do smaller, like negative 10 to the 18 up to like, so just take the lowest point on the lowest rectangle. So min I y j I. So it's like the min I. So do you have a t lower and t upper, which are the lower and upper bounds of the cal positions? Um, yeah, so you have like t lower, which is the lower bound for the minimum y, and then you have t upper, which is the upper bound for the maximum y. But the key thing that you should see is that it's always optimal to have positive slopes for a prefix and negative slopes for a suffix. So essentially, you're solving two separate problems. So for everything that has a negative slope, uh, you're trying to maximize the uh, highest intersection. And then this is like some binary search. When you maximize the highest intersection, it's like a binary search in the range y max. T is in the range from y max to infinity. And then when you're binary searching for the min intersection, so max intersection, it's a binary search over t from y max to infinity. And then when you're finding the min intersection, it's a binary search over the t from negative infinity to y min. How many possible values of t? Um, uh, it should be able to pass if you set infinity equals to like 10 to the 18. Because when you're binary searching, the number of times you have to run it will be like log 10 to the 18. Although I think it depends on the inputs. Like I think so the slopes, they can be up to 10 to the 9. Yeah, and then the coordinates can be up to 10 to the 9. So you have to binary search. Yeah, so the upper bound of t is going to be 10 to the 18. So I'm just having this infinity here. You're binary searching in the range from y max to infinity. Um, so the upper bound, yeah. So yeah, so you're binary searching in the range from y max to 10 to the 18. Yeah. Yeah, so yeah, we're trying to find the min, yeah, we're trying to find the you're trying to minimize the maximum intersection of the negative slopes and then maximize the minimum intersection of the positive slopes. What are y max and y min? So I define y max to be the largest y values out of the rectangles you give, because you know that there has to be a cal that's above the largest y value. Um, yeah. So yeah, yeah, yeah. Okay. Any other questions? Are the numbers guaranteed to be integers? The slopes are guaranteed to be integers, but the uh when you're binary searching on x, these upper bounds, basically the upper bounds for the slope, they're not necessarily going to be integers, so you'll need to handle that with like floats or something. Okay. yeah, I'll move on to problem 3. Yeah. Sorry. Okay. Yeah. So yeah. Problem 3, I'll say I felt is more standard. Um, yeah. So this is marbles. So Bessie and Elsie are playing a game of marbles. And Elsie, yeah. So Bessie holds out A marbles and Elsie has to guess if it's even or odd. And if Elsie is correct, she wins the A marbles from Bessie. And if she guesses incorrectly, then she loses A marbles. Yeah. And basically Elsie wants to have the basically Elsie keeps announcing even and odd and wants to make the lexicographically smallest sequence such that no matter what Bessie does, Elsie will still win. Yeah, this is problem 3. I believe someone else will be presenting too. Um, yeah. Um, yeah, so this is asking to find a lexicographically minimum turn sequence so that Elsie will not lose regardless, no matter what. And yeah, basically uh Elsie can Elsie can see the Elsie knows for each turn what the K yeah, Elsie knows for each turn what marbles Bessie might pick, right? Yeah. So yeah, so I guess here there's uh Elsie has 10 marbles and there's 3 turns. Yeah, and then Bessie can make 2 potential moves. Yeah. These are the potential moves Bessie can make in each turn. So the optimal answer is even, even, odd. I guess if you pick even, then Bessie will pick the worst case, which is odd. And then if you pick even, then Bessie will pick worst case, which is odd. So Elsie will lose 2 marbles. And then at the end, yeah, Elsie can just pick odd, right? Yeah, so I'll explain about problem 1 later if we have more time. But yeah, let's yeah. Yeah, I'll answer questions about problem 1 later if there's more time, but let's go over the idea for problem 3. Uh, so let me go back to the OneNote. Mm, Yeah, so in the ideal case, since we want lexicographically smallest, then Elsie can just keep guessing even, 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 since that's like the lexicographically smallest string you can make, right? So there's M turns, right? Um, so basically, let's yeah, so let's do the following kind of strategy. So wishfully you want to keep guessing even. So let's say you guess even. You're only allowed to guess even if you know that if you know for sure that you want there's a way to not lose no matter what Bessie does. So basically if I yeah, so I can guess even if I know that in the next turn, I'm going to lose no matter what. Sorry, I'm going to win no matter what. So let's consider how we can check if we're going to win no matter what. So let's say I have K marbles left. So basically the optimal kind of play, if I want to maximize my number of marbles, which will tell me whether or not to pick even, oh, I should pick even. I should pick even if after I picked even, the number of marbles cannot drop less than or equal to 0, right? So basically, let's think about what's the optimal strategy. So if yeah, so if Bessie's um so if all of them are like even, like let's say k equals 3, right? And then all of them are even, like 2, 4, 8. Then you can maximize your marbles by guessing even. And if all of them are odd, like let's say, so if you guess even, then Bessie, if they pick the worst case, then you'll gain 2 marbles. And if all of them are odd, then yeah, then you can just pick odd, and in the worst case you'll get 1. And the other case is where you have even and odd elements, right? 7 and then 4. So if you pick even, then Bessie will pick this odd number and you lose 7. And if you pick odd, then Bessie will pick uh, the largest even number and you'll get -4. So it's optimal to pick odd. So basically, for you consider like if you have things with different parity, you consider, so if you have things with different parity, so if you have even things and odd things, then you consider the largest number and you pick the opposite parity. So in this case, the largest number is 7. So if you want to maximize your chance, like if you want to win and minimize your losses, then it's better to pick, um, oh, sorry, I flipped it around. It's better to pick even. Yeah, it's better to guess. Wait, no, I was correct. Yeah, it's better to pick odd, because you'll only lose 4 in the worst case. If you pick even, then you'll lose 7 in the worst case. Yeah. So this is kind of the optimal strategy. So basically now we have like an O of n squared way. It's too slow to pass everything, but this is O of n squared idea. So the idea is play even whenever you can, when it's possible, uh, when uh, you can win. Otherwise pick odd. Like you play even when you can, and if you check whether you can win the rest of the game. So you have K marbles left, then you play the game optimally. By if everything's even, pick even, and if everything's odd, pick odd. And then if there's 2 different parities, then just pick the one that minimizes your losses. Then you initially have K marbles, and your score over time might fluctuate something like this. And you basically win if it's always greater than 0, right? So you win if the score is always greater than 0, no matter what Bessie does. But this is too slow. But what we can do is we can speed up this checking if we can win the game with K marbles. Um, Essentially, we want to find the minimum prefix sum. And right, so if like first you might have a loss of +4, you have a gain of like 10, and then -20 or something. Basically the minimum prefix sum will tell you whether the game will be lost. So you basically win if k is min prefix sum um, is strictly greater than -k, right? So if you lose more than k, then if you lose at least k, then you're going to lose. So basically, we can do like a dynamic programming. So it's basically a DPI is like min prefix sum of gains. Yeah. So yeah, so DPI is the min prefix sum of gains when playing optimally, like using the strategy to like lose the least or gain the most. Yeah. So this we can compute DPI, right? Because the first case is you play even, and then the second case is you play odd. So yeah, if you play even, you'll get some gain of like xe, and then if you play odd, you'll get some gain of xo. So yeah, uh, yeah, so yeah, you'll have like dpi, um yeah, uh, so xe, or basically your delta, it could be negative or it could be positive. Um, um, Maybe it could be zero. I'd have to think, but it's basically the minimum. It's like the minimum prefix sum. So it's gonna be min of um like whatever you gain, and um and then I guess in the beginning you also have prefix sum of zero, and then x plus dp I plus one. Right. Yeah, so that's how you compute the minimum prefix sum, just because when you're making your ith turn, then you have like some gains and losses from the I plus one's turn, and the minimum prefix sum from the I plus one's turn translates to x plus the minimum prefix sum, because there's this x here. And then there's a possibility that the minimum prefix sum is actually attained in the very beginning, right? Or maybe the minimum prefix sum is attained after you get the first move. So you'll have this kind of transition. dpi is min x0 and x plus dpi plus 1. Yeah, so the strategy should be like play even when you can win the rest of the game. Otherwise pick odd. And now we have a very easy way to see if we can win the rest of the game. So let's say we pick E at time step I, then we have some kind of score S, right? And then, or I guess, yeah, we have K marbles left after we play E. Then we can win the game as long as dp I plus 1 is strictly greater than negative K. So if it's strictly greater than negative K, then it's still possible to win the game. So we want to pick even. Um, Otherwise, we should pick odd. Summarize this. So for many of these problems where you want to find something that's lexicographically minimum, we have even is less than odd. So it's always good to be able to pick even. It's always better to pick even. If you have a choice between even and odd and both are valid. Yeah, so basically the idea is you try to pick even as long as it's possible to win the rest of the game. And if you can't pick even, then you can pick odd. And to check if it's possible to win the rest of the game, um, you have to check given the optimal play strategy, whether um, whether the like the total number of whether the total number of marbles is strictly greater than zero the whole time. And this is basically looking at the min prefix sum of gains, and you can compute this using a DP. It's like a suffix DP. And if you have K marbles after playing a turn, then you're going to win as long as dpi plus 1 is greater than negative K. So yeah, computing the DP and then deciding between even and odd, this will be O of n. Yeah, any questions? Um, yeah, I guess I'm done with problem 3. But yeah, can you summarize? Yeah, sure. Yeah, I can summarize the solution ideal. So this is question 3. Yeah, so you want to find the lexicographically smallest sequence so that you can still win. And the idea is like you can build the solution answer one by one, and it's always optimal to pick even over odd, because that's just like that will just make your thing lexicographically smaller. So we want to check if it's valid to pick even. And yeah, there's an optimal strategy. We pick even if it's possible to win the rest of the game without having zero marbles. And you always, if you know the parity of what Bessie has, so if you know Bessie always has even, then it's better to guess even. And if you know Bessie always has odd, then it's better to guess odd. And otherwise, if Bessie has a choice, then you pick which one will uh will suffer the least losses. Yeah. So in this case, it's better to pick odd. And you want your minimum prefix sum. So basically, your losses will be like some kind of ups and downs, and you want your minimum prefix sum to be high enough so that this never hits 0 from k, and you can compute that using a suffix dp, which is the minimum prefix sum of gains when you're playing optimally. Yeah. So this is like an O of 1 dynamic program. And when you're picking even, yeah, you can just look at your DP to check whether it's still possible to win after picking even. And if you can't pick even, then you should pick odd. Yeah. Yeah. Wait. Max, I think you're next. Problem 2. Oh,
All right, can everybody see me and sorry, hear me and see my screen? Everybody see me and sorry, hear me and see my screen. Can I get like a confirmation in the chat or something? Okay, audio's a little weird. Not sure if I can actually do anything about that though. Let's see. Uh, is this a little bit better or not? Okay, if I have background noise, then we might have a problem. Yeah, my apologies. I don't think I can actually fix my mic issues right now, but am I at least like understandable? Okay, that's nice. All right, so as Arvin said, I'll be going over the second problem for silver, which is test tubes. In this problem, Bessie basically has two test tubes, and each of the test tubes is filled with a certain combination of liquids. These liquids do not mix, and they have different colors, which Bessie just calls colors 1 and 2. And these test tubes have infinite capacity, but in the beginning they're each filled with n units of some mixture of the two liquids. So since the liquids don't mix, once they settle, they divide into layers of like separate colors. So because of this, the two tubes can be viewed as strings, where like each index of the string is just a color of the tube. So Bessie wants to separate these liquids so that each tube contains contains like all units of a particular color of that liquid. And the way it works is that she can pour like every layer of a certain color of liquid into a different tube, and she also has a third beaker that's also infinite capacity that initially is empty. So your goal is just to figure out the minimum number of like pours it takes Bessie to like sort the colors into different tubes, and then at the very end, one of the tubes has to contain like all of one color, and the other has to contain all of the other color. And then the beaker at the end also has to be empty. And you also have to construct a solution. You have to like figure out the exact sequence of moves. Obviously, in most cases, there are going to be multiple possible sequences, so outputting anyone is fine. Yeah, let's just jump into the solution right away. We are running a bit low on time. So a few basic observations for the sake of simplicity, it doesn't really matter how much of a color is like in a row in a tube, only like what colors at what positions in what order. So in other words, each tube is like actually functionally equivalent to either like 1 2 1 2 1 2 1 2 something, or like 2 1 2 and 2 and 2 1 and blah blah. I'm gonna wipe my mic. Honestly, I doubt that's an option. but I will try. Any better? Okay, a lot better. Alright. So our goal now is to find a lower bound, and for the answer, simply to make our lives a lot easier when it finds to be greedy. So first of all, intuitively, the answer cannot be lower than the number of quote-unquote switches in the the color in the test tubes. Whenever two opposite colors are adjacent, the top one has to be poured out, right? Like, let's say we have a 2 on top of a 1. We have to pour the 2 out because there's probably some 1 somewhere else that we have to pour into the 1, or if they like get the 2 into the other 2. Like, no matter what, if two tubes are in the same, if two colors of a liquid are in the same tube, we're going to have to pour one of them into the other because the tube can only have one color, right? So let's let the number of switches across both test tubes, like in total, like number of color switches called X, then the answer is at least X. If we do a little like just tinkering around, we can find that we can actually raise the lower bound a little bit. Let's consider the case to the right? Our test tube has size 2, and the first one is color 1, 2, and the second is 2, 1. So no matter what we do here, we can't actually get better than 3 moves. We're gonna have to move like one of them into the third test tube, no matter what. Like, even if there are only 2 switches, the answer is going to be 3, because let's just say we do the sequence like 1, 3, and then 2, 1, 3, 2. The 2 in the first test tube has to move into the third tube, and then it has to move back to the second tube later. So it takes 2 moves instead of 1. Ooh, my mic is wonky again. Yeah, honestly, I don't even know at this point. I apologize. So yeah, but like generally in this case, we can just extend this to all cases where there are at least 2 switches, because if both like color switches are in the same tube, at least one color is gonna have to be part of the third tube, which would add a move. And if the 2 switches are in different tubes, like 1 switch in each tube, then it's just the case shown above. And obviously this applies to like if there are more than 2 switches as well. And then we can actually raise this lower bound a little bit higher. Consider the following case, right? 2, 1, 1, and 1, 2. Even though there's only 1 switch, the answer is 3, which as you might know is actually 2 higher than the number of switches, not 1. And this is because not only do I have to move the 2 into the third beaker, but we also have to move one of the 1s into the other tube, right? We have to pour the bottom of the tube into the other tube, and we have to move something in the third tube and back. So again, this also just extends to any case where both test tubes have the same color at the bottom, because no matter what, the color at the bottom is going to have to be poured out, and there's going to be some color on the top that has to go into the third test tube, right? So to recap, if both test tubes share the same color at the bottom, the answer is at least X plus 2. And if they do not share the same bottom, but there are at least 2 switches, the answer is at least X plus 1. And if neither of these conditions are satisfied, the answer is at least X. Does that make sense? Alright, so now we're just gonna have to find a solution that actually meets these lower bounds, or at least very close to it. So the first thing to observe when we make the solution is that there's no point in dumping 2 different colors into the beaker, because that doesn't actually save you any moves under any circumstances. Because first of all, like let's say we dump 2 colors into the beaker, we're still gonna need 2 pours to move them both out. So we may as well just like pour the top color into like whatever tube it was supposed to be in, right? And if we pour 2 colors, it doesn't actually free up another like color underneath both the tubes to be poured either. Like if you do like a lot of playing around with test cases, you'll just realize that eventually, like, there's really no point in like freeing up 2 colors. Can I send the link for the slides? Yeah, no problem. Actually, can I do that afterwards? Like after I present? Yeah. So, yeah, as I was saying, it doesn't actually save you any moves to like dump 2 colors into the beaker. So no matter what, the beaker's only ever gonna have 1 color at one time. So we can just like, when we're sorting through the test tubes, we can greedily dump 1 color into the beaker and dump the other into the other test tube. Does that make sense? Yeah, alright, so just going like the way we construct a solution now. So like for sake of simplicity, we'll just assume that the first test tube has less switches than the second, and the bottom of the first test tube is color 1. If the top of test tube 2 is color 2, dump it into the beaker. And then now we go for test tube 1. If the top is color 1, dump it into tube 2. Otherwise, dump it into tube 3. And you don't dump out the bottom. And you do the same for test tube 2, right? If the top is color 1, dump it into tube 1. Otherwise, dump it into the beaker. If the bottom of test tube 2 is the same as the bottom of test tube 1, dump the bottom into test tube 1. Otherwise, just leave it there. And then at the end, just dump test tube 3 or like the beaker into tube 2. And then at the end, tube 1 is going to be all color 1 and tube 2 is going to be all color 2 and the beaker will be empty. So if we look at this algorithm carefully, it meets the lower bound for earlier, right? Because each switch, each color is dumped exactly once. And can't you only dump the top? Yeah, my meaning is basically you just take the tube one at a time. Like you go through each layer. If like the top layer is color 1, if the top layer is like color 1, we dump it into the other tube. If the top layer is color 2, then we dump it into the beaker. And then yes, this actually is going to be exactly the number of steps that the lower bound we calculated earlier, right? Because each layer from each tube is dumped exactly once. And if you put anything in the beaker, it's going to add 1, which is going to be the x plus 1 bound we got earlier from 2 switches. And if the tube 2 is of the same bottom, it's going to be plus 1 again, so that's going to be the x plus 2 bounds that we got earlier for having the same bottom. Does this make sense? All right, then I'll just hop into the implementation now. Then, all right. So here is the code in C++. Yeah. So at the beginning, we just take in the input, and then as we noted earlier in the slide, like we assume without loss of generality that the first test tube was shorter and that the bottom of the first test tube was color 1. But like obviously, when we're actually writing code, we're going to have to make sure that the test tube we're treating as first actually is the shorter one, and that the bottom we actually do to like treat the colors differently depending on what the bottom of the shorter tube or the test tube 1 is. Yeah, so this is what we're doing here, right? While we're in the input, we're sort of like sorting the tubes. We don't care about multiple colors in a row, so we only like, I guess, like push it into our tube if it's actually a switch in color, right? So if tube A has less switches, then we treat it as the shorter tube, and otherwise what are A2 and B2? A2 and B2 are just like the character strings that are in there, and A and B is like the stack of things that I do. Because like remember how I said it earlier, like we don't actually care how many like 1s or 2s are in a row. It's like functionally equivalent to like 1 1 or 1 2, right? So the stacks are just like 1 2 1 2 1 2 or 2 1 2 and 2 1, and the A2 and B2 are like the actual input value that they give you. Yeah. So I guess this is like the meat of the code here. This is our solve function. So A is going to be our shorter tube. It's going to be like our test tube 1 from earlier. And B is going to be our larger tube. It's going to be our test tube 2 from earlier. So AID is just like which tube the shorter one is, and BID is which tube the longer one is. It's just like make actually re-clean, please. All right. Any better? It's a little bit better, yeah. Okay, my bad. Alright, we are running a little low on time though, so I guess I'll just continue. Yeah. So back to the function. A is like our shorter stack, and B is our longer stack. AID and BID are like just there for constructing the solution. And bottom is the color of the bottom of the shorter tube. or tube 1. So our stack C here is just like what representing what's in the beaker at any moment, and our vector ops is just like the solution we're constructing. So first of all, at the very beginning, we're going to deal with the edge case where it's just 1, 1, and 1, 2 in like the 2 tubes, because our code actually does kind of crash there. So we're just going to take care of that test case immediately, and the answer is 0, obviously. Yeah, and then as we started, like, if test tube 2 is a different color from from the bottom of test tube 1, then we dump it into test tube 3, or the beaker. And then we just go through test tube 1. If it's the same as the bottom of the test tube 1, then we just dump it into the other tube. Otherwise, we dump it into the beaker. And then we do the same for test tube 2. If it's equal to the bottom of test tube 1, then we'll dump it into the other tube. Otherwise, we'll dump it into the beaker. And at the end, if the bottom of test tube 2 is the same as the bottom of test tube 1, we just dump it into test tube 1. And then if we have stuff in our beaker, then we just dump it from the beaker into test tube 2. And then we just return our constructed solution. This is basically exactly what I explained earlier, yeah. So returning to the bottom here, yeah, so basically the way we call our solve function here is that if stack A, or like the first input, is shorter than like the second test tube that they give you, then we'll just plug it in as normal. Like A is the shorter tube, and B is the longer tube. But if B is like longer than A, sorry, if B is shorter than A, then we plug in like B as the shorter tube, and so on. And obviously like the bottom accordingly too. And yeah, and then we just output the answer. Does anybody have like any questions about the code? All right, if not, I'll just end it here, and then I guess if you have any questions, just slide it in the chat.
Okay, thank you. We do have a brief presentation from xcamp, if you want to start that. And then if you have any more questions, feel free to put that in the chat. And then our instructors will answer.
Yeah, so yeah, one second. Yeah, so xcamp has like a USACO report. So basically you can write how many test cases you passed for each problem. And then you'll get like a report card emailed to you with some details. Yeah. Yeah, so it's still in development for the February version, but yeah, encourage people to use this for the January version. You can find a link here. Yeah. Yeah. That's all I had. Yeah. Thank you.
Okay, thank you all for coming to the workshop again. And then that should be the end. Again, feel free to put any questions in chat, and thank you for coming.